Okay. Okay, we're live. Okay, so welcome everybody. This is a webinar number 86 of the Latin American Webinars in Physics. My name is Joel Jones from the PUCP in Peru, and we're very happy that you're all here. Today, we're having Oscar Vives from his lecture from the Universidad de Valencia. And as a fun fact, he was my PhD advisor. So you can imagine how nervous I am right now. Right? So, okay, let me tell you some stuff about Oscar. So Oscar did his PhD in Valencia, and then he's done quite a couple of postdocs before coming back. He did a postdoc at Brookhaven, then that followed with another postdoc at CISA, then at the University of Oxford, and finally at CERN. Then he came back as a Ramón y Cajal, which is basically a tenure track in Valencia, and is now a full-time lecturer there. So we're very happy that Oscar is here. So Oscar will be talking to us about supersymmetry. We're still interested in supersymmetry. And how we could actually test it in the MoEDAL experiment, which maybe you haven't heard of. So it's a good time to learn many things about many things. So, okay, I'll leave you with Oscar. So we're all yours.
Okay, thanks a lot to the organization for inviting me to give this talk here. And well, as he was saying, I am a lecturer in Valencia. In fact, I am theorist. I'm not experimentalist, but I do collaborate in the MoEDAL experiment. So I will do you a talk about the phenomenology of this experiment. So I think I should start. Let me share the screen. Yep. Okay. It's okay? Well, let's start. Okay, the title of my talk, as you can see, is Searching for SUSY long-lived particles at MoEDAL. So this is based on several works. In fact, here there is a proceeding of some conference last year or this year, but we are finishing the paper now at this moment. So let's see, what do we have here? First, what is MoEDAL? MoEDAL is the acronym of monopole and exotic detector at LHC. It's a detector whose main motivation is to look for magnetic monopoles. However, as we will see, the characteristics of this detector made it useful also to look for other exotics. Basically, as we will see, highly ionizing slow particles. Let's see if we can use this detector to search for supersymmetry, exotic supersymmetry, I would say. The detector you can see in this figure is in the LHC cavern. It's a small detector, basically this part here, where you have a main to compare, which has several components. Here, you have a low threshold nuclear tracking detector, which is a nuclear tracking detector is basically some stack of plastic sheets where that can be ionized if some heavy or slow charged particle crosses along them. But this low threshold nuclear tracking detector has a threshold for zeta, the charge, over the beta, the speed of 5 to 10. Okay, the same, a high charge catcher nuclear tracking detector, which a little bit higher with to catch the particles, and then there is a time pixel, some radiation detector with pixel detectors that can control the passing of some charged particle. And then there is a monopole trapping detector. Let me tell you something about the low energy threshold, low threshold nuclear tracking detector. This is composed basically of some plastics, some individual sheets of plastic, all stacked one on top of the other, such that when a charged particle, heavy or a slow charged particle, traverses them, they ionize and leave a track in these plastics. These plastics are a passive detector. We do not see the particle passing through these plastics, but we just leave it there in the LHC cavern for 1 year, basically. When they stop, we take these plastic sheets away from the detector, we replace them, and we bring them to some laboratory in Italy, in fact, where they are treated chemically to enhance these tracks, these holes that the particles had made through the plastics. So then, as there are several sheets of these plastic detectors, you can reconstruct the trajectory of these charged particles through the detector. Normal particles do not leave, normal charged particles do not leave a track in this detector. So there is basically no background. The difference of this detector with other detectors is that it's basically a passive detector. You just leave these things there. You have no trigger, you have no computers to read the results at the moment, but they just accumulate all the events during a long period. It's the largest deployment of nuclear track detectors at an accelerator, and also trapping detectors. So this is the MEDAL experiment. How does it work? Well, as I was saying, these nuclear tracking detectors, they are ionized when some charged particle passes across them. Basically, it's the Bede-Bloch formula, where you have that the energy deposited in this detector is proportional to the charge set, the charge of the particle. This set is the charge of the nuclei, the capital, the small set is the charge of the particle, and beta, the speed, okay? So, for instance, a magnetic monopole has a very large ionization. In fact, is 68 would be this factor, 68.5 square. So, a magnetic monopole produced at LHC would leave immediately a huge hole, a huge signal in this detector, in this NTD. Okay, but at the same time, a heavy charged long-lived particle, charged evidently because it's proportional to the charge, the effect, and it must be slow. So any heavy charged long-lived particle, in principle, can be slow. And if it's slow, if set over beta is large, it leaves a track on these NTDs. In fact, this is very different from, as is obvious, it's very different from ATLAS and CMS. In particular, the main points of this kind of detector is that we have no trigger. In ATLAS and CMS, you have a lot of events, of spurious events, if you want, uninteresting events, and you have to build a system of triggers to keep only the data that can be interesting to you. This is the trigger system. For instance, for SUSY, would be large missing energy. We have no problems with timing. And in fact, the background by electrons, muons, and all normal particles, even protons and all these things, leave no track at all in this nuclear trapping detector. So it must be really something slow, which in the energies of LHC means heavy, and charged. For instance, we could detect better doubly charged particles if they are long-lived. They must arrive to the detector, okay? But these particles is the kind of particles that we are going to search for at MEDAL, okay? So which kind of particles in SUSY? Well, obviously, as you know, in supersymmetry, the only stable particle, if R parity is conserved, supersymmetric particle, should be the neutralino. The neutralino is neutral, so it could not be detected by MEDAL. But we can have some situations where exotic, if you want, exotic situations where these charged particles are long-lived in SUSY. For instance, leptons. We can have the stall in gauge mediation with gravitino LSP, long-lived, lighter supersymmetric particle, or in the coannihilation region, even in the constrained MSSM, if the mass difference between the tau and the neutralino is smaller than the mass of the tau. In this case, we could arrive to, say, C tau of the order or larger than 1 meter, which is what we need because our detector is basically 2 meters from the interaction point. In the same way, we could have R hadrons, which are metastable gluinos or squarks in a split SUSY that hadronize. In the same way, in a split SUSY, as the rest of the particles are very heavy, the gluinos are metastable, or stops with are the NLSPs with gravitino as before the LSP. Or in anomaly mediation, for instance, charginos. Normally, in anomaly mediation, the LSP is the neutralino but Wino. So that the chargino, the lightest chargino, is degenerate with it. In all these cases, we would have some heavy, or can be heavy, supersymmetric particles that could live long enough to arrive to this nuclear trapping detector. The problem is that we need a high ionization we are sensitive to Z over beta larger than 5. This means if charge Z is 1, that beta should be smaller than 0.2 or of the order of 0.2. It's approximately, okay? And that is a problem. Let's see. For instance, this is a simulation that we made some time ago that we produce, for instance, pairs of staus of mass 1 TeV or higxinos or gluinos of mass 1 TeV. And this is the distribution in arbitrary units, just normalized number of events in the distribution of beta for all these particles. We are sensitive to betas smaller than 0.2. As you see, if we produce staus, which are the particles that we are interested, the problem is that only of the order of several 10 to minus 3 is the number of particles to which we are sensitive. The rest of ones, the heavier, well, fastest ones, we would not be sensitive. However, if they are higxinos or gluinos, we are of the order of 0.02, 0.03 for these of these particles slow enough to produce a signal at MEDAL. So this is what obviously we cannot detect. In this case, it would be very difficult to detect these slow moving staus because most of them are faster and would not leave a signal, but probably could leave a signal in other experiments. So it would be easier to see them, for instance, at ATLAS or CMS, probably. Depends also on the triggers, as we will see. So that's what we will do. We study stars, long-lived particles, stars, but after gluino production. Okay, we produce them with a gluino. The gluino has a beta small, or relatively much smaller, it's much flatter distribution. So a good percentage of them is slow enough. This decays to one star, and then the star has the beta, the velocity of his parent particle, if it's not much lighter than the gluino. So that's what we will study here. So the first problem is that we are somehow, in some sense, competing with ATLAS and CMS. And as I was saying, we have some advantages with ATLAS and CMS, that ATLAS and CMS need to have some triggers which normally would not be sensitive to these particles, to these slow particles, because the normal triggers they use is large missing energy, high PT, etc., etc. But in the last years, there have been several studies where they try to look for these long-lived particles. For instance, I have here classified them as searches of displaced jets. That is, they see a pair of jets which do not point to the interaction point, but to another point at a certain distance of the main interaction point. For instance, in that case, this is an example. Here I have the two most recent papers, these two. One is ATLAS and the other CMS. I don't remember which one is which. And this is the triggers and the conditions on the signal of one of them. For instance, they need missing energy to trigger this case, missing hadronic missing energy larger than 180 GeVs. It's a good trigger, but in this case, in principle, we could have no missing energy because for us in the detector, the tau long-lived would be detected as a muon, and it's not missing energy. But if it's slow enough, first, it can arrive later than it can arrive after the next collision has taken place. So things start to mix and things like that. But well, in this case, what they are using is this hadronic missing energy larger than 180 GeVs, the mass of the displaced vertex, because they will look for jets, pairs of jets that form an interaction point isolated from the main interaction point. The mass of these jets must be larger than 10 GeVs. This is to eliminate some background. And then the distance of this displaced vertex in the transverse plane, in the XY plane, must be between 0.4 centimeters, 4 millimeters, and 30 centimeters. And these are the triggers of these papers. In our case, as we will see later, we could have cases where these triggers do not find or charge particle. Another one is searches of displaced lepton pairs. An R is missing here. There are 3 papers here. Basically, they trigger on a muon signal or missing energy larger than 75, and a jet of PT larger than 110, and then the distance of the lepton pair in the transverse plane larger than 1 centimeter. And then they also, in these cases, require also hits in the silicon and semiconductor tracker. These things, as we will see now, made possible that as we have no trigger at all, some of these conditions will not be satisfied by our events, some cases, in some SUSY models, and they will not detect our models, while in MEDAL, there is no problem. We have no trigger, we have no timing, we have no problem of this. So it can be detected at MEDAL and not at ATLAS and CMS. This is what I will say. These papers, these are recent papers, they are being included in the new analysis and next analysis for the paper that we are preparing now. But at present, I don't have these results yet, so I present some results of a previous, the proceedings we presented some time ago. It's from one paper, a little bit old now. It's on 2013 at CMS, but things have not changed that much. These are the kind of triggers or that they use to, or the selection they use to select the events. For instance, the red ones are the interesting ones for us. PT, the transverse momenta of the jets or the particle, must be larger than 45 GeVs. The distance in the transverse plane must be larger, this should be larger, not smaller, than, I think it should be larger than 0.5 centimeters. And then they need at least, for these events, they need at least 1 pixel hit, which means that basically this particle must hit the detector at a distance smaller than 20 centimeters or 30 centimeters. I don't remember now the exact number. And then the same with tracker hits, etc. So what kind of model can we have that these constraints or these conditions are not satisfied while it can leave a signal at MEDAL? Well, we are looking at these kind of processes. We have, as I was saying, we are interested for reasons of number of events, basically for the cross-section, production cross-section, and for the beta, we are interested in production of gluino pairs. We could produce a gluino pair with a relatively degenerate neutralino. So the gluino would decay to neutralino and 2 jets. And then the neutralino would decay to the STAU and 1 pion. For instance, if the mass difference between neutralino and the STAU is relatively small, this would be just the constrained MSSM in the coannihilation region with a relatively heavy neutralino. That is true, but we have already looked at the normal models. This is an exotic model, it's true, but we have to look for exotic models nowadays. So in this case, we could have a long-lived neutralino in the neutralino STAU coannihilation. Then the STAU would decay later, for instance, to a gravitino. If we have a long-lived neutralino, long-lived enough, we can have no pixel hit. And the constraint was at least 1 pixel hit. 1 pixel hit. That is, if the neutralino lives long enough to decay away from the pixel detector. Then the STAU would decay to a gravitino or a singlino in the next to minimal MSSM. In this case, we would have this thing. I should not show these exactly these plots because these plots are not present constraints. These are future constraints. These are the CMS, the previous constraints with 150 femtobars. It's close to what we have now, and this could be with 300, this green region. So MEDAL with much lower integrated luminosity, because we are at LHCb and then they reduce the integrated luminosities, would be able to find this region. So in fact, in all this area, if we take away the the green part, because it's future, and we don't know exactly how it will work, we would be able to find for gluinos of 1/400 and mass of the gluino minus mass of the neutralino 30 GeVs. Okay, we would be able to find this signal, and ATLAS and CMS would not be able to find them, at least CMS. This is okay, but we can do slightly better. We can have, in a little bit more exotic model, a long-lived neutralino, but still a large mass difference with the star. And in this case, we would have, apart from the pixel hit, a kink in the detector. In that way, they would not be detected at ATLAS and CMS. In this case, we would have this area, which would be detectable at MoEDAL and not at ATLAS and CMS. Notice that we have an advantage. Here, n equal 2 means that we require only 2 events. We could even require 1 event, but to be safe, we say 2 because we have no background. Only one clean track through our plastic detectors, macrofoil detectors, would be enough to say that we have a charged long-lived particle. So we could increase this slightly. This is a logarithmic scale, so not much, but a little bit. And in this case, we could be able to detect this star much better than ATLAS and CMS. Anyway, even if we find something here in this area, our detection system is completely different from ATLAS and CMS. So we could confirm, or they could confirm our discovery independently with a completely different procedure. So it's a very interesting experiment in this way. Okay, so this is basically the way this detector works, and an example of what can be done. But let me tell you something about some recent signal of possible long-lived particles. I don't know if you know the ANITA experiment. It's a balloon experiment in the Antarctic, which looks for polarized radio emission from the electromagnetic component of cosmic ray showers, and in fact tau leptons. They look at tau leptons. They can distinguish these long-lived cosmic ray showers coming from underground, from the Earth, or from the top. They have made 4 flights, these balloons, of 30 days at some height of 30 kilometers, and they have, well, there are some differences between ANITA 1, ANITA 3, and ANITA 2. ANITA 4, we don't have still the events. But they observed 2 anomalous events with some energy of 0.6, and these are exa electron volts, I think, 10 to the 9 GeVs, going through 6,000 kilometers in the Earth, both in ANITA 1 and ANITA 3. This is basically the events, the flight path of this balloon, and the different characteristics of this event. This is not possible in the MSSM. With these energies, the mean free path of these particles, of some charged particle, or some neutrino through the Earth would be only 100 kilometers. But we are seeing steep events that cross basically 10,000 kilometers. So could it be a heavy supersymmetric charged particle? That was the one question in some paper. If it's a heavy supersymmetric charged particle, for instance, as tau, the mean free path is 10 to the 4th kilometers. In 10 to the 4 kilometers, interactions slow it to rest. And for a tau of 500 GeVs and a lifetime of 10 nanoseconds, it's basically 6,000 kilometers. And they decay close to the surface. And tau would decay close to the surface for angles of the order of 120 degrees. So in principle, this could give you a tau here, a tau decay here, producing the cascades seen by Anita. This was an explanation by some paper some time ago. The problem is that there could be other experiments. For instance, ice cubes should see a factor of 10 more events than Anita, and it has seen only 2 events similar that could be similar to these events if they are misidentified tracks with 70 peta-electron volts. But what we are interested is if we could produce these heavy charged particles. Well, as these are saying, the authors are saying in this paper, these are not possible if they are too heavy if you produce them through electroweak interactions, and the cross-section is too low. But as I was saying before, this is exactly the kind of process that could be produced in metal detected if they come at the end of a gluino chain. So this was one of the motivations, or possible motivations, for this paper, that we have some possible signal that maybe metal could detect in the future experiments. So in this case, we would have an tau of 500 GeVs, between 500 GeVs and 1 TeV, and we would need a lifetime of 10 nanoseconds for this tau. We have a gluino of 1 TeV, and the mass difference between the gluino and the neutralino and the gluino and the tau smaller than, well, tens of GeVs. Metal could detect this event. This is exactly what I was analyzing before for the kind of chains that we have. Okay, obviously these taus in Anita are produced through neutrino interactions, while at LHC they could be produced at the end of a gluino chain. And if the cross-section is large, that is, if we have a gluino production, the cross-section is large, then we could detect at metal. At some point, we could be able to find also electroweak production of these events. Just when we have enough statistics with something of, well, I don't know if it's close to 1 TeV, but we could be able to find the direct production of these stars. So this is what we are doing now. We are trying to see if we can do a complete analysis of these kind of events as a motivation. It's just an example at metal. And this is basically all I had to tell you about the metal experiment. As I was saying, metal is a new experiment. It has already been there for several years. We have some results for monopole searches, some limits on masses of monopoles, which must be light to be able to produce them at LHC. They cannot be GATT monopoles, obviously. They must be light monopoles, but they appear in some theories, more or less exotic, but okay, we have to search for them. We have already from ATLAS and CMS very strong constraints on metastable SUSY particles, but it is possible that metal can improve this thing. As I was saying, we have a possible signal of tau production in high energy cosmic rays, and Anita has seen at least 2 events compatible with taus of the order of 1 TeV. So in principle, if we produce them through colored particles, through gluinos, for instance, metal could constrain these processes and say if these Anita events are real or not. This is basically all I wanted to tell you. Thanks.
Thank you very much, Oscar. It's been a fantastic talk. It's been super interesting. So let's see if there are questions from I think I forgot to mention it. at the beginning of the webinar. So everybody who is listening on YouTube, you know that you can ask questions directly via the chat that you have on your right. So please go ahead if you have any questions. Remember, there is a 30-second delay, so please don't be shy and ask your questions already. Great. So there are currently no questions on the live system. So maybe there are some questions coming from the other participants of the webinar. Let's see, maybe Roberto or Alejandro have questions. Okay, so I'm going to start. So first, do you know if this is more of an experimental question, but do you know if MoEDAL is put next to LHCb on purpose, because you have LHCb having a lower luminosity, right? Mm-hmm. So the question is, okay, is it done on purpose that you need a lower luminosity to be able to?
No, it's not. We don't need lower luminosity. We could cope with much higher luminosity, but it's very difficult to put this thing inside of the ATLAS cavern or the CMS cavern. There is no space. While in LHCb, well, I don't know if there are also some political reasons, or they want to. Okay. We need someone to leave us put some detectors, and they have to have the space also. But no, I think is that only for sure at ATLAS is impossible. Have you been to the ATLAS cavern?
Right. Well, I mean, so I guess also that it's related to LHCb being more or less like being half a detector, right?
Yeah.
In the sense, not half a detector, but you know what I mean, right? That the interaction point is at one edge of the detector instead of at the middle, right?
Yeah.
Because I think that in the future they plan to install these phaser experiments, phaser detectors that are like downstream, but they're for larger decay lengths, right?
Mm-hmm. Yes. I don't know exactly, but in principle, yes. It's just we do not. This experiment does not take a lot of space. It's just relatively small. At least the passive the nuclear tracking detectors is nothing too large. It's just I guess they could even build another detector outside of it. The only problem is that we need to take out the plastic parts from time to time. But apart from that, in principle, they could build a detector around all.
I see. Oh, that's interesting.
If we can enter,
you could enter to take it out. Great. Okay, super. So before I continue with the other questions, maybe there's another question here from the audience. Yes, Roberto has a
Joel.
Go ahead, Roberto.
Okay. I didn't listen to the part. Oscar, I like it a lot, your webinar, your talk, and I wanted to ask you do you expect in MoEDAL to get also some kind of signature from exotic matter not coming from the accelerator, for instance, cosmic rays or very long-lived monopoles going around?
Well, the problem is that we have a very small surface. Obviously, we are a small experiment. Yes, in principle, if something arrives, but should be something multiple or charged and slow. It has to probably go through some meters of Earth. I don't know if we could get it from outside. I think, cosmic rays, probably they arrive still, but I think we are too small. For instance, at Ice Cube or the ones in the Mediterranean and these things could see it better. No, they could leave also a signal there, just the Cherenkov radiation, probably.
Yeah. So, for instance, I mean, MoEDAL is not for that, but it would be feasible, for instance, to put a similar detector in the International Space Station, something like that, to catch things
Well,
that are
in
not
fact,
interacting with the atmosphere.
now that you say it, yes, there, well, in the, I don't know in the space station, but they were talking some time ago to put some of these detectors in some high mountains in Canada. One of the researchers here is from Canada, from Alberta, I think. And they were putting these kind of detectors for cosmic rays, probably, in some high mountains also. I don't know exactly how it is, the project at the moment, but yes, there was some suggestion to do it. From outside, you know, the problem, for instance, in the ANITA experiment, what we have is high energy neutrinos arriving to the Earth, but they are so high energy that with the interaction with the nuclei of the Earth, the crust, they generate a tau because they have they are PeV, so they generate a tau with even in the center of mass, they have enough energy to generate a 500 or 1 TeV tau. And that's what we see then in the, it can cross the Earth because the interaction with the Earth is smaller if it's a tau, and it decays exactly at the other side where the detector is with this ANITA. That was, so if they are neutrinos, the high energy cosmic rays, no, we would not see them, obviously, because they are neutral. But there could be some other things, yes, in the atmosphere.
Mm-hmm. Okay, thank you.
Okay, so we have a question from Diego Restrepo.
Okay.
So he's asking, what are the requirements for a general vector-like new lepton to produce a similar signal?
Well, in principle, it's the same thing. The problem is, well, or problem, if you want, signal anything charged, which is slow enough, could leave a signal, okay? If it's long-lived, it must be long-lived because it has to go 2 meters away from the interaction point. Then it must be charged. If it's multiply charged, better. But if it's just charged, just singly charged, then the beta must be relatively small. Is what I was showing in the plot. Well, at LAC you have different partonic center of mass energies, and so you get a distribution of betas, if you want. And most of them are fast. So you need something, if they are heavy enough, obviously they are slower, but you produce less. So it's a little bit of, you have to play with these things. So in principle, yes, we could, if they are long-lived, these vector-like particles, we could detect them, no problem. But probably they could also be detected at LAC. That's why we had to look for something a little bit more special, because if it's just a charged particle going through the LAC, you will see it in the pixel detector, in the silicon tracker, in the muon detector, and everything, or in the hadronic calorimeters, everything. So you would just see an extra particle. What we have is some model, some points in some SUSY model where you can evade these triggers of ATLAS and CMS. So yes, if you have a model where the vector-like particles are long-lived, maybe there is some symmetry that protects them, and then you produce them such that you can evade the triggers, we could see it because they cannot escape us. We have no triggers. But we have to escape the triggers from ATLAS and CMS. That's the only thing. But in principle, yes, we could see it. If they are produced and long-lived, they arrive, yeah.
Okay, so we have to wait 30 seconds for Diego to do a follow-up question. So maybe meanwhile we wait, so I would like to ask you, I didn't really get the difference between the two plots. In one of them, you had a pion on the final state, and the other one you had a tau. So what is the role of the tau there? I didn't really get it.
No. The thing is that, well, that is, it was some way to, let me put it again. I didn't put the signal here, but okay. Share screen, okay. Here. Well, in this one, the thing, this one, you have a pion, you see? But this is because the mass of the neutralino and the mass of the tau are smaller, the mass difference is smaller than 1 TeV. If it's smaller than 1 TeV, it cannot decay to a tau and a neutralino, and a tau. No? Because you don't have enough energy to create a tau and a tau from a neutralino, if the mass difference is smaller than the mass of the tau. Okay? So, which is the next one? But is the pion. A pion and a tau. If you want, this would be neutralino going to, let me see, tau, and then you need two quarks from a neutralino, well, from a...
Yeah, it's...
well, yeah.
You produce how is it again?
This, tell me the truth, to tell you the truth. It should be, in principle, a tau and a tau, but a virtual tau. And the tau would decay to a pion, for instance, pion and neutrinos.
All right, yeah, that's it.
And in this case, the difference was that we were interested in evading some other of the constraints of ATLAS and CMS. In this case, we were requiring that the mass difference is larger between the neutralino and the tau, such that the tau, because it can decay to a tau now, the tau gets part of this energy and the tau is kinked. It's not the same direction as the neutralino. It's a different direction. So in that way, you could try to reconstruct the direction of the tau, which are jets, if you want, and the tau, which is just a muon for the detector, if it arrives to the muon detector, it's just a slow muon, basically. And you would get at them, and you would see that they do not point to the interaction point. This would be, this is in the analysis that the CMS analysis we were analyzing here. As I was saying, this, if you now apply the constraints on displaced lepton pairs, this could be, because for them, lepton pairs are just muon pairs and electron pairs, not tau pairs. This could be a little bit strange, but okay. If it's some not normal signal, they are not prepared. They have to look for them explicitly, and this is what we were doing here. In that case, as we have a kink, a change of direction of the charge track, if you want, or well, not charge track because it was neutral, but these do not point to the interaction point. And in this case, it escaped the triggers that this experiment had. That's the difference. But in this case, you see the mass difference between these are 300 GeVs. So the tau can take quite much energy and make a change of direction of the tau. The problem here is you need some extra way to ensure that this neutralino is long-lived, because with such a long, a large mass difference and well, with such and this channel open, you could, the normal thing is that it would be short-lived, but you could try some kind of symmetry to make it long-lived. So, but not a standard. This was just an exercise, if you want.
Right. All right, because you want the neutralino to be long-lived, so it leaves no trap.
So it does not hit the pixel detector. Another problem, typical problem we have here, obviously, this is an exponential decay law. If the lifetime is, say, 25 meters or 20 meters, there is a percentage of them that will decay at 1 meter or less than 1 meter. So there are always a tail. There is always a tail that this is why these arrive so high in these cases, because there is always some that decay inside the pixel detector and give a signal, depending on the lifetime and on the mass. Okay.
Right. Okay, so the only constraint is for it to not decay within the pixel detector. It can decay elsewhere within the tracker.
In this case, yes, basically the thing that we were using here is no pixel hit. Yes, this means decaying away from, I don't remember, it was 20 or 30 centimeters.
I see. Okay, yeah, because then yeah, if it was away from the tracker, then you would imagine that the neutralino would decay after the metal detector, right? But if it's after the pixel only, then okay, maybe you have more space.
They need at least 1 pixel hit, so they require 1 pixel hit. That is a normal requirement. Many of these here, in the others, more. This one, for instance, requires between 0.4, which is clearly inside the pixel detector, up to 30, which is also 1 pixel hit. Okay. This must decay in the pixel detector, at least 1 pixel hit.
I see.
The same thing. These are such as one of these 2 experiments. These are requirements for them, their analysis. But they need these things because to see that the jets are correct, they need or they require that they have some signal in the pixel detector, some signal in the silicon tracker, and some signal in the hadronic calorimeter. It must be consistent. If not, it can be some other thing.
Yeah.
So this is the thing they have and we do not have. And that's the advantage, although they are doing very well, I must tell you. And I thought it would be much easier.
Right. Great. Super. And okay, so that's all my questions. I don't know. There's no more questions on the live chat. I don't know if there's any more questions from the audience here. And oh, Alejandro saying something.
No. I just no. Thank you. No
question. Oh, sorry. You muted yourself. Okay, so that's it then for today. Let me before closing, let me remind everybody that we still have more webinars. The next webinar will be on the 20th of November. We'll be having Eliu Huerta giving a talk. I'm not sure about the topic, and that'll be webinar 87. So anyway, Oscar, thank you very much once again for the talk. It was really great, really interesting, and well, hope to see everybody again soon.
Okay, thanks a lot. Yes, see you soon.
Okay.
Bye.